All right. So first of all, we have an integral over two elements. So from 0 to 2. For simplicity, it is usually very desirable to split this integral into a summation of integrals, each integral over just the one element. Okay, in this case, we're going to split it into integration from 0 to 1, f of x minus ux squared plus integration from 1 to 2, f minus u squared. And over each element, we know that u is a linear function, right? So that can be represented into f of x. Okay, in the first element, we know that the function is what? Is u1 minus u0 times x plus u0, right? So this is what the function look like in the first element, and then what the function is going to look like in the second element. From 1 to 2, we have f of x minus, in this case, u2 minus u0 times x minus 1 minus u1 squared dx. So this is what the function look like in the second element, the second linear function. All right. Okay, so what's next is really just performing these integrals, right? So if you perform these integrals, you are going to realize u1 and u0 are just the numbers. They are not a function of x, right? So they can be pulled out of the integrals. And you're going to see that what happens is that you get a quadratic function of u0, u1, and u2, right? Because there is a square on top of it. So what you end up with is an optimization of a quadratic function. So here, basically, the square, when you see these numbers, sorry, u2 minus u1, okay, when you see this u0, u2, u1, it's not, we don't know the coefficients yet, but we already know it is going to be a quadratic function. All right, and if you take the derivative of a quadratic function with respect to the, well, variables of the quadratic function, what do you get? What happens when you take derivative of a quadratic?
Linear.
Yeah, you get a linear function, right? So you get a linear function. So this is basically a linear function of u0, u1, u2, that's equal to 0. You get another linear function of u0, u1, u2 is equal to 0. And a third linear function of u0, u1, u2 is equal to 0. So you get a three linear equations, and you have exactly three unknowns, u0, u1, u2, right? So three unknowns, three equations, you solve them, you get my u0, u1, u2. That uniquely determines what this function is, right? Uniquely determines what this function is, and you get your best approximation. So this is basically a complete walkthrough of what finite element method does. Okay, again, you set a bunch of constraints, and the constraints make sure that you can uniquely prescribe what the approximating function is using a finite number of parameters. For example, in this case, u0, u1, u2. These numbers uniquely determines what the approximating function is. And then you are asking not just for any approximation, but a best approximation in some sense. In this case, I'm defining best as the approximating function that minimizes the average, the square, the discrepancy between the function to be approximated and the approximating function. That turns into an optimization problem of minimizing that scalar discrepancy, right? By choosing the best parameters, the best finite number of parameters. And that optimization problem, by taking the derivative and set it to 0, becomes a set of linear equations for me to solve. By solving these linear equations, I obtain the parameters that uniquely determines the approximating function, and I'm done. This is the solution. Okay, James, you have a question?
Yeah. So in all the equations, you have the integral of x squared. So why is that quadratic instead of cubic?
So are you asking why the j is a quadratic function of u0, u1, u2?
Oh, of u0, u1, u2, not of x. Right. Yep. Okay, that makes more sense.
Yeah, not of x. Yes, because these integrals are actually integrals over fixed domains, right? So they come out to be just the numbers. If you're able to pull these u1, u0, u2 out of the integral, I mean, if you expand the square, pull the u0, u1, u2 out of the integral, then the integral are just the numbers you can evaluate.
Okay, that makes more sense. Great. Thanks.
Right. Yeah. So here we didn't actually construct the matrix. We're going to discuss that in more general sense later. How do you construct the matrix? It's going to be kind of you're going to be programming something to do that, not doing that by hand. Okay. But this is I'm just giving you the idea of how finite element method works.